First of all, I wanted to thank Ramona and Nevada County Media for hosting our meeting tonight. It's great to have this facility. Also, we've just completed our SMPTE election for the 2025-2026 year, and we have our results, and we have some new board members I wanted to introduce. First of all, John Henkel will be our new chair going forward, so thank you very much. Cindy Zulsdorf, who's remote, is there on the screen. She also will be joining us as the new secretary treasurer. So thank you, Cindy.
Thank you.
And as far as managers, which are a 2-year term, John Leron is staying on board with us for a second term. So thank you, John. And Ian Foster is here joining us for the first time. Thank you very much, Ian. Admit somebody. And also Ian Godfrey, who's not here, has joined us for the first time with the first term. So we're very, very happy to have those guys. And they join current managers, Jed Deem and Victor, who's here tonight. Thank you, Victor. And we have one, yeah, thanks, Victor. Cut it short. We actually have an open position that still has a year on it. So if someone's interested in helping out, or maybe just kind of learning how things go, being around with this crowd a little bit, let us know. We're happy to have you join up with us. I also just want to do a quick recap of what we've done for this, held meeting-wise for this past year. It's been a pretty good run of meetings, I think. We had our social meeting here at the museum, which is actually now going away. Ramona's hosted the museum here, Tech Museum, for 4 years maybe, but now it's Grass Valley's taking it on and moving it to Montreal. So we'll have a nice museum there. We had an IPMX presentation by Jed Deem. We've had 3 AI presentations so far. It's been our main topic this year. One with Roy Folkman, another with Tom True from NVIDIA, and in March we had Carl Paulson, and now tonight, of course, we'll have our 4th one with Matt. We also had cloud workflows with Robert Erickson, and media distribution, the media distribution mess with Chris Lennon. So pretty good round of meetings. Also wanted to let you know and remind you that all the meetings are recorded and they're posted to our YouTube site. If you go to YouTube and just search on Sacramento SMPTE, you'll find it. So if you want to see something that's happened in the past, you're welcome to go there. As far as meetings going forward, we take a hiatus during the summer. So this is our last meeting for the SMPTE year, and then we start up again in the fall, usually with our annual social meeting in September. And I'd like to introduce Matt Connolly. Matt Connolly is a senior embedded systems engineer at AJ Video Systems, where he develops high-performance video and audio hardware for professional media applications. His career spans military, aerospace, and startups with a focus on systems-level design and real-time embedded computing. He began his professional path in U.S. Army Special Operations as a reconnaissance and technical surveillance specialist with the 3rd Ranger Battalion. After completing his engineering education, he spent several years working in the aerospace sector in Southern California, contributing to engineering projects for organizations including NASA, Disney Imagineering, the U.S. Navy, and Mooney Aircraft. Matthew moved into early-stage technology companies in Austin, Texas, where he worked on underwater robotics, human-computer interaction, and machine learning applications in embedded systems. His work has consistently bridged the gap between hardware, software, and algorithm design. He brings a multidisciplinary perspective to embedded engineering and has a particular interest in making advanced tools like machine learning accessible and practical for engineers working close to the metal. So with that, I'd like to introduce Matt, and thank you very much for that.
All right, thank you for the awesome introduction.
Do you want this for your mouse?
Yes, please. Thank you guys all for coming out tonight. This is going to be probably a little different than most of the presentations that well, I know they are. There's been a couple of these presentations. This is going to be very in the weeds, but at a level that anybody should be able to access. And if you have your laptops here, you can follow along with this presentation. It's a Google Colab notebook. This notebook allows me to have markup documents where I can walk through all these concepts, but also have these code blocks where you, me, anyone that has a link to this document can execute this code in the browser, and it runs on a remote Google server. So we're going to be doing a lot of at least 6 different model train-ups tonight, where we're going to train artificial intelligence models, and it's stuff that normally would probably make your fan cook your computer. It won't do it here because you'll be running it somewhere else, and you don't have to worry about package management or environment, none of that stuff. It's just going to run right there in the browser. If you don't have a Google account, you will not be able to run the code, but you'll still be able to watch, look at the document. All right, so we've got a lot to get through. I'm going to get to it. Welcome to Machine Learning AI Fundamentals for Media Professionals. This course is designed to give you a practical, hands-on introduction to core concepts of machine learning and artificial intelligence using TensorFlow, one of the most widely used frameworks in the industry today. I designed this course to be accessible to everyone. So somebody who's never written code in their life and somebody who's been writing code there all day today should be able to look into this and kind of get insights into what this offers. And what I'm really trying to give you all today is an introduction to some basic tools that you can easily access, that you can go and build things with. When I got into this like 5 or 6 years ago, I knew nothing about machine learning, and I, within 2 weeks, had spun up my first machine learning model and saved my startup and gave it another year of runway, and then we crashed. But but we did some really great stuff in that time. Let's get into it. All right. By the end of this, I'm going to teach you core principles of machine learning. I'm going to show you how to use TensorFlow and Keras, which is also part of TensorFlow. These are Python libraries that can basically make it more accessible to build and design machine learning models. I'm going to explain to you, or you're going to understand how common ML and AI techniques apply to media workflows. And you will all, if you have this open in your browser, you'll be able to design and imagine your own AI-powered media applications. And even if you don't have it in your browser, you can open this later and go through it at your leisure. So we're going to start with core concepts. But first, I'm going to update my TensorFlow, JAX, and NumPy libraries. You don't necessarily need to do that. That's a safeguard against later stuff in the program here. Okay, so machine learning is a sub-branch of AI. AI is the hot topic. The last couple of presentations I've been to for SMPTE have been about AI at a very high level. This one's going to be in the weeds, as I mentioned earlier. ML is basically in traditional programming and development. We are given data and we create rules to generate answers. ML flips that. With ML, you give a machine data and answers, and it generates the rules for you, which you can then take and plug into your algorithms and generate the answers. If that doesn't make sense, here's a little diagram kind of showing how machine learning programming is in contrast to classical programming. Some key concepts: artificial intelligence. It's the broader field name. Machine learning is a subset of that. So we're going to talk about different things tonight. You're going to hear me say training data a lot. That's the breadth of stuff that you train on. So when people talk about, like, I'm trying not to invoke transformers tonight because we're not going into that subject. I will talk a little bit about it. And TensorFlow does cover transformers now, but it didn't up until I think a year or two ago. But when we talk about training data, it's like a bunch of data that you use, and you throw at the machine and say, like, here's everything that you could possibly learn on. Go and figure patterns out. Features and labels. Features are the input data. Labels are the explanations of what the input data is. That will make more sense as we get into some examples. The model is the thing you train. Training versus inference. Training is the act of feeding the data into the model and saying, go learn some stuff. Inference is when you take that model out into the real world and you say, all right, here's something you've never seen before. Give me an answer from that. All right, types of machine learning. I'm not going to go too into depth on this, but machine learning obviously is loosely modeled after human learning behaviors, right? So we train machine learning models through experience, repetition, and feedback, which are great analogies for how these processes actually work. There are a couple different types. We have, okay, supervised learning, flashcard. This is the dog, and what a dog is. Unsupervised learning, I give you 5,000 images of random stuff, and I expect you to just sort them out yourself and put them into groups. And you just kind of figure it out. It's basically finding general features across things without saying, this is this. And reinforcement learning. Reinforcement learning is essentially like training your dog. Like you tell it to sit, and if it sits, you give it a treat. If it does anything else, you just kind of ignore it. Why this matters in media. So one of the big takeaways I'm trying to get through in this, that hopefully I'm kind of conveying, is I'm giving you guys, if you're not into this already, I'm trying to give you guys access to some tools here which you can turn around and use in your everyday lives to make new products, make new technologies. A lot of these things, even though these are not the flavor of the day transformer type AIs, these are all things that have tremendous value opportunities for you to develop new technologies within that can be placed in like an embedded device or at a more bare metal level. So stuff you can develop now that could bring more value to the company you work for, or maybe you start your own company. Who knows? We're going to start talking about some core machine learning algorithms. We're going to talk about regression, clustering, hidden Markov models, and basic dense neural networks. I'm not going to spend a ton of time on these, but I just want you to kind of loosely understand what they are, and I'll show you some examples. So linear regression. Linear regression is, if you have used trend lines in Excel, then you've used kind of linear regression. You've done linear regression, and I forget how they do it in Excel, but wrote it down somewhere here. They are using, I wrote this down, the mathematical formula anyways, okay, hold on. Okay, I didn't write it down. Well, okay, so Excel is using like pure mathematics to develop this trend line through data you have plotted. When you use TensorFlow or Keras to do it, it's using iterative optimization, so it's guessing over and over again to generate trend lines. It's doing the same exact thing, but it's doing it in a completely different way. Now, I know this will be a running theme throughout this presentation, wherein I'll show you a demo, and you'll be like, why would I spin up a bunch of servers somewhere and train this data on a thing to solve this problem that I could solve with like 3 lines of code? That's completely valid. These demos are designed to kind of show you how to do them, and then you can take these kind of concepts and apply them to far more complicated applications. So for instance, when we do the reinforcement learning, I'm going to show you how to make a little character navigate across an ice field that you could literally write, I think, in like 5 lines of code, and you would solve it every time. But you take the same application, put it in a car, instead of the agent, you make it the car, and you put all the inputs to be cameras and sensors, and now you've got yourself a self-driving car model. Okay, so linear regression. So here we have some code right here. I'm gonna go through it real quick. I'm gonna generate some linear data. I'm gonna introduce noise into it. I'm going to here's some parameters where I can control how many and how much noise I put into it. Generate linear data. And here's where I'm going to train a dense sequential linear regression model on this. I'm only doing one input, one output, because it's y equals mx plus b, is the formula for a line. I'm going to compile the model with stochastic. Don't get hung up on these words. If you're not interested in this, you can go more into the links that are in this presentation later and learn more about stochastic gradient descent and a lot of this stuff. But basically just know that these are rules that we're using to tell the model how to learn. And there are different rule sets that you can use to change the way that the model learns. And we'll just run it. So we're going to run this code. Feel free to change any of these parameters if you're running the code on your own machine. Run the code. What we got down here? All right, there we go. So as you can see in my code up here, I've also got some plotting mechanisms so I can show you what happens here. So what I've just done is I've used machine learning to train a linear regression model through a bunch of randomly modified data. And what we're trying to do is get back to the core function, which was the core parameters of the function, the rules, if you will. The machine learning model came with a slope of 2.26 and a y-intercept of 0.99. The slope was 2 and the y-intercept was 1. So we're not super close, but we're close enough, and I didn't do a bunch of training on this. This is a very short training session. But I just want to give you an idea of like how this general process goes and how it'll go, and also I needed to test the code and make sure it's going to run live in the program here. All right, so clustering, we talked about unsupervised learning. Clustering is where you send a bunch of data points into this model, and it's going to find centroids for where the based on how many clusters you define for it. So for this, I've gone ahead and I generated random data, and I ran the machine learning model on it and generated these centroids from it. And then it turned around and labeled each one of those data points for me. So this will make more sense when we start getting to neural networks, because as a neural network, in the midst of a neural network classifying things, it has to sort them into groups. And this is essentially that under the hood, where you're getting to see some of the later stages here where it decides this thing that I've seen that has all these features fits closer to this kind of classification as opposed to others. Hidden Markov models. Hidden Markov models are when you run your phone and you voice to text and it interprets what you're saying. It's a state-based machine learning algorithm that essentially uses phonemes to infer things about the state that is coming next or the possible state that it can be in. It's a really hard thing to show in a demo here. The demo that I had up until last night, and I decided it was way too convoluted to try and explain to people, was I could show you a sequence of actions that were observed, a person's daily routine over the course of a week. And they go out, they go running, they go to the market, they go to work, kind of thing. And from that, you can infer what the weather was based on just observing the actions of the people. So it's a way to infer hidden states from observed states that are correlated to one another. So that'll come more into play when we talk about reinforcement learning, because once again, reinforcement learning is training an agent to take actions based on the state. It's very state-based. So when you need things that are time sequential or have a order to them that matters, pretty much all these are built on a hidden Markov model under the hood, or have a hidden Markov model as a component of it. All right, and that's where we come to basic neural networks. I'm keeping on time here. All right, neural networks inspired by how the brain works. They're everywhere. The image recognition, they were basically the big. They're used everywhere. I mean, image recognition, audio recognition, video recognition, any kind of media, any kind of data. And that's what you should take away from this: is any kind of data that you have that has patterns that you can observe, but it's really difficult to write rules to classify or to identify. Neural networks are great at that. If you kind of escape the notion of like, I'm trapped in this particular dimensionality, you can start to really unlock some really fascinating abilities to get features that correlate across spectrums, which hopefully I'll be able to explain a little bit better here. So neural network, things that are good at detecting faces in a frame. Here's the neuron formula, if you care. Oh, sorry. So the neuron formula, the output of a neuron. So a neural network is made of countless numbers of these neurons that are divided into layers, which allow features up at the input layer to trickle down and get classified and create categories that then tell a final layer, I have all these features that are reminiscent of this thing, so I'm probably this. And it does it when we train these, it's training by guess and check, essentially, and building these neurons to have weight and biases to them, so that it puts more emphasis on certain neurons to respond to features that are observed. It's like a small math processor, and each one of these neurons has its own little math module inside of it that does a specific type of math, usually defined for the entire layer. So I'll show you here in a second. So here's I love this picture example because this really kind of communicates it really well. What we have here, in 3 dimensions, you've got a number 3, right? This is a super old example of a dense neural network. You got this number 3, it gets flattened from a 2D array to a 1D array, which are your first layer of neurons. The features from these neurons get passed down, and through constantly updating the training process, the values of each neuron, you can build to basically emphasize these neurons are important to me when I want to recognize the number 3. And those get passed down. One of the output ones that says, hey, this thing that I'm looking at has all the features that I recognize as being the number 3 because I've been trained that this is what this looks like. We're going to go ahead and build one here right now. We're going to build an image classifier with a dense neural network. Doing good on time still. Okay. So now that you guys hopefully understand this, and if you have questions while we're training the model, I'll allow some questions real quick. I know we're moving really fast and there's a lot here, but I'm hopefully kind of making some sense. Yes. Yes, that's right. Yeah. Yeah, I put a lot of words in here, and then I was like, there's no way I can read all this. So I'm trying to just kind of communicate it as best I can here. And once again, you should all have access to this link, and if you don't, there are links on your desk here that will take you to that document. You can just look it on your phone, and you can read it later if I'm going too fast, which I am going too fast, but I am aware of it. Okay. So what we're going to do in this code is we are going to load the fashion MNIST data set. Nobody cares what that acronym means, but it just means a bunch of pictures of clothing items. We're going to split it into two groups, our training sets and our testing sets. When you train a model, you have to give the model data that it can look at over and over again, and then you have to test that model by giving it data it's never seen before to test if it's actually learning. A model can overlearn from the things that it's been taught. That's called overfitting. And once you have an overfit model, it's essentially useless because it'll never be able to interpret new data. What you want is a model that can look at data it's never seen before and come to the same conclusion. We're going to real quick write the names of these things because you need them later, and I'll show you why. Essentially, the outputs will be a tokenized version of this, an array of 10 outputs, and we're going to see a probability distribution in that 10D or that 1D array of 10 entries, and the highest number will be what the model thinks it is. So real quick, I'll show you what these images look like. So we've got a sandal, clearly, and an ankle boot. Some really high quality images here. We've got a, whatever this is, pullover. This entire 600,000 data set, sample set is composed of images like this. You're looking at this and you're like, when I used to do these, I used to call this the Minecraft version. Low resolution stuff. Whenever you're building a model, you have to kind of experiment with, does the thing that I'm looking for, and usually this is something you can kind of infer by knowing about the data, but you have to look at, is the thing I'm looking for easily recognizable in a lower resolution presentation, or do I need fine detail in order to find the things I'm looking for? And you make those trade-offs and you can scale, you shape your data accordingly. But as you can see here, we don't need much data in order to determine if it's a sandal or an ankle boot. However, we'll see in a second, that'll come back and bite us a little bit. And in each one of these cells, these are probably hard to see, but each one of these cells is a value from 0 to 256. We're going to go ahead and bring all to a 0 to 1.0 normalization here shortly. We're going to set up a simple dense neural network, a single layer, and dense neural networks are typically one layer. This is usually a smaller part of a larger model, which we'll get into in the next section, convolutional neural networks, and I'll explain why. Choosing the number of neurons in a layer. I could sit here and tell you that there's a really good reason for why you select a certain number of neurons in the next layer beyond the one you're on, but but in the words of Dr. Rick Sanchez, science is sometimes more art than science. Many times I've seen, I can't tell you how many Stack Overflow hosts I've seen where people are like, I don't know, I want to create a script that just randomizes the number of neurons and then retrains the whole model with that and just get me the best output. Sometimes you don't know. However, I encourage anybody who gets really into this, go follow the link after and go into the documentation, and you will learn more about the math, about how this is all working. And it goes back to that thing where if you know the data you're looking at, you kind of know the things that you're looking for in the data, you can a little bit guide neurons to be the correct number to properly condense the features you're looking for into a usable output. But for now, we're just going to say, just pick a random number that's less than the number of input neurons that you're doing. Okay, so summary for this model, we're using 128 neurons in the hidden layer. You can do more or less if you want. This has to be less than the input layer. The input layer, these images are, I believe, 28 by 28 arrays. So the input layer is 28 squared. Nope, that's not right. 784 input. That's not right. Well, either way. We'll have it set up in a second. Okay, so here we're setting up the model again. So we're loading the data set. I split it into training data and testing data. Usually want to use like an 80-20 split. So 80% of your data used for training, 20% used for testing. We're going to normalize the pixel range of each value. So we're dividing everything by 255 to bring it to the 0 to 1 spectrum. We're going to define our sequential model here, which we're putting 3 layers in. We're defining right here our flatten, which reduces the input layer from 28 by 28 to one single 1D array. I know this is a lot. I appreciate you guys being patient with me. We're creating an intermediary layer, a dense layer of 128 neurons using a rectified linear unit activation function. And that is basically a nonlinear mathematical process so that your response is not linear on each individual neuron. So it makes your learning, the way your neurons learn and the way they react to new inputs not aggressive. So if they see a new input in an area, but it's not something that it's seen a lot of times, it will downplay the amount of response it applies to that neuron in its training process. And then we have our output layer here, which has an output layer of 10 neurons. And 10 because we have 10 clothing items. So we're going to watch this on the output, and it'll be able to tell us what the classifier thinks it's looking at. And we're going to compile the model by specifying, we're specifying the optimizer and the loss function. And so optimizer is the algorithm that updates the model's internal weights to improve predictions. And the loss function is how far off the model's prediction is measures how far the model's prediction is from the actual value. You can really get into the weeds here. I'm trying to brush through this quickly. So we're going to run this. We're going to compile. Okay, so we're downloading all our data. Okay, we should have it. I think we're all done here. We are. So we've built our model is compiled. Our model is defined. Our model is compiled, and now we're going to train it. So we're going to feed the training data in, our X training data, our Y training data. So this is supervised learning. We're telling the model, here's a bunch of pictures, here's what they are. And we're allowing it to train over time and build these out. But we also have this other data set, the testing data set, that we're going to throw at it later and be like, here's some stuff you've never seen before. Good luck. This is going to take a while, presumably. So while this is training, are there any questions? Yes.
How do you keep learning training?
There are mechanisms that you can employ. There's code you can write here where you can put safeguards in to check if the loss value. So, okay, you're watching here, if you have a loss is decreasing over time. If you see the loss value increasing, that means that your model is overfitting. So it's overtraining. And at that point, you usually put a safeguard in to stop it. You're like, oh, if you see that, revert back, go to the thing right before you started the loss prediction drop. And you can put different factors in to say, like, if it happens 3 times, do it. Usually I do it at 1. I'm like, there's no reason to play with fate like that. Now, we just trained a model right here. We just trained a neural network right here to be able to recognize images. And it has the final accuracy that's reporting is 88%. The loss of 0.295. We had consistent decrease in loss across all training iterations, epoch, if you will. If I was training this model for real, I would have put the safeguards in to make it stop if that loss started to climb back up. I also would have added 2 to 3, maybe 4 zeros to that. Because based on how I've set my learning algorithms, that can take as long or as little as possible. And the longer you train it, typically, unless you see that loss result go high, the better the model gets. So we could have presumably got this model to go even longer. And feel free on your computers to change the epoch number to like 100 and see what happens. A lot of times I'll plot the loss function at the end, and it's very common to show the loss function line. Okay, so now we're going to evaluate. Now we're going to take all that test data that this model has never seen, and we're going to throw it at it and be like, tell me what you think this is. So glad we fixed that code thing. I was a little worried. All right. So what do we got here? We have got, we've done the evaluation. Looks like the resulting accuracy across the entire test set was 87%. 87% is not incredible, but it's not bad. You usually want to look for like a 99%. If you do that, you get raises at work. So we got it. I pulled one sample out to show prediction on it. It predicted to be a shoe. It was in fact a shoe. I also generated this thing, and the code's in there. Feel free to use this because it's one of my favorite things to use in training. I just generated what I call a confusion matrix. I don't call it that. It's called a confusion matrix. And what this is, this shows every single data point, or every single feature that we fed into that for evaluation, and shows what the model thought it was. So on the left here, we have what the thing actually was. And in this, on the bottom axis here, we have what they thought it was. So there's a lot of really expected behavior here for something that generates an 88% accuracy, right? It sees a shirt, or sorry, it saw a pullover, thought it was, or sorry, saw a shirt, thought it was a pullover, and vice versa. There's a lot of confusion there. These things look very similar, especially in a low resolution image. We maybe could have improved that by training more, maybe not. Maybe we need to go get higher resolution images. Hard to say. So that's the first neural network. If you ran the code, you just built your own neural network right there, and you can go and modify them, do whatever you want. Okay, so cool. Done dense neural network. That's the first step into the neural network spectrum. Now we're going to talk about convolutional neural networks. The difference in this. So if you look up here, the shoe, these there we go. This pullover. Sorry, I almost called it a shirt because I'm not a very good classifier. This sandal, this ankle boot. These are all frames, right? They're all in the spectrum here. They're very confined to that perspective and that border. What a convolutional neural network does is it takes these concepts. I want to say this right. So if we had trained a model on 5,000 pictures of a dog that was looking to the right, and then we fed it a picture of a dog looking to the left, you would not know what that is because it has no concept of pooling features and then reclassifying them into sorted groups, right? A convolutional neural network does that really well. It essentially takes individual feature tracking like this and then builds subcategories that a final layer looks at. And once again, I talk about it's important to escape the notion of dimensionality, or once you get down into the 50th or 60th layer of your model, it's not looking at this is an eye anymore. It just knows dogs have two eyes and they'll be spaced generally apart and with this relationship to a nose kind of thing. But it's very abstracted at that point into a neuron that just represents that relationship. That's all this is. We're just essentially stacking abstraction on top of each other, and down at the very bottom, the final layer is just seeing weird features that happen to correlate to certain things. What we're going to do with our convolutional neural network right here is we are going to classify. What are we going to classify? We've done some shirts, we've done some shoes. With our CNN, we're going to classify. Oh, the other thing, things called TensorFlow. I got asked it the other day, like what kind of tensors or what dimension tensors are we using? This goes back to dimensionality. You can maintain the dimensionality of your data when you pass it in. You can flatten it. You can work across multiple spectrums, like an image or video is an image is a three-dimensional array essentially, right? RGB data in a 2D spectrum in those three dimensions. You add a fourth dimension, you got video. You can feed that all into a CNN. You can feed in a single frame. You can feed in a sequence, whatever you want. If you can escape the notion of dimensionality and just say, I have data and I've reduced it to a blob, and they're a uniform blob, you're more than welcome. You can feed that in, and 9 times out of 10, you'll learn some stuff from it. The model might be able to pick up what you're looking for, or you might find that there's no commonality between the things you're looking at. So for this one, we're going to load a data set that has airplanes, automobiles, birds, all these guys right here. And they're color images, so they're three-dimensional. They have a 2D spectrum, and then they're going into the third dimension of RGB. Each one of those, 0 to 255. And the same thing, we're going to, okay, I actually need to load this data. This is going to work properly. Okay, yeah. Okay, so I'm going to load my data here. I'm splitting my training and testing data sets. I'm normalizing it right here to 255 or to 0 to 1. And I'm creating my class names. That's going on there. I'm going to show you one picture of a horse. There we go. A picture of a horse. But these are the kinds of images we'll be classifying. Here is, so before we set up those 3 layers, CNN is split into two layer types. You have your dense neural network on the tail end that does all your final processing. That's why we taught that one first. In addition to that, with a convolutional neural network, you build a front end called a convolutional base, and that is usually where you put your meat and potatoes of your feature tracking. So the model we're building today, you can see here, we're building a sequential model and we're adding layers. We're doing a 2D convolutional, so we're keeping the spectrum of these. We're doing a max pooling. Max pooling layers are essentially where you take these initial features and you pool them into a subset, and that's what I was talking about. Like, they're abstracted now. It's just a layer of nodes that represent. This is an eye that I saw somewhere in the image, right? And some of those things can represent. This is an eye that I saw up in the top corner of the image, or an eye that I saw down in the bottom of the image. That's what you'll see in a lot of the. You can see it here. I add a convolutional 2D layer. I add a max pooling layer. I add another convolutional 2D layer to sort that max pooling layer, and then I create another max pooling layer. And then I add one more convolutional 2D layer that's going to feed into our dense neural network backend, essentially. I'm going to define that. I'll talk about the layers here. This is a quick summary of the model. So you'll see parameters on the bottom here. This is important if you're the kind of person that thinks, I'm going to want to go take this model that I built and put it in an embedded system, or build a tensor core in HDL. This data will tell you how many nodes and how many pathways your system is going to have. It's a really good way to forecast the size that your model will be if you had to put it in something small and fast. And it's essentially just taking stock of all the connections between the different neurons in each layer. But we're adding more. But wait, there's more. Much more? Much more. Okay, define that guy real quick. So we're going to add our dense layers down. We already did that in the last one. I showed you how to do this. We're putting a 64 neuron layer, dense neural layer in there. But before we do that, we're flattening it out of the 2D that we had, and we're just making a single line. Dense neural networks work a little bit better with a flat line. We're going to define that guy. And here's the real definition of our model at this point. So this has our convolutional 2D front end on it, and it's got our dense neural network back end on it. And that value right there is the value that if you were trying to compile this out into an end product, that's the value you'd want to be looking at. All right, so parameters, yeah. Okay, so we're going to train this model. This one's going to take a while. So I'll go ahead and fire this up. We're using the same atom optimizer. We're still using a sparse categorical cross entropy. Logic, I forget what this actually is. It communicates the outputs are raw logic. I don't know what that is. I put that note in there and I don't remember what it is. Okay, and then we're through what our training actions. You can see right here, when we're training, I'm going to output the accuracy. Now, hopefully this will be true, but what you'll notice a lot of times is you can run the same model 7 or 8 times and you'll get different outputs because a lot of this is randomized under the hood. We're doing 4 epochs. Still going to take a while. Any questions? I'm sure there are some. Yes.
So when you were doing
yeah,
is the math any more complex? It looks like it was like per filter essentially on the data.
Yes. It's essentially just a bunch of little FIR filters, like all just clustered in together. The math is very compartmentalized and basically uses tree structures to connect them all together, and that's why it's easy to implement because you don't really have to get into define too much. You still have to define it for the layer, but you don't have to define it for each individual neuron because that would be obscene and probably result in something unusable. However, people who get more deep in this are always like partially define layers so that a lot of the image classifiers that we use in modern day have been carved up like that so that because they come to understand like, oh, this feature is actually picking up on, or this layer is picking up on these features, and we want to make sure that this kind of learning algorithm is applied to those features specifically, but only in certain sectors of the array. And so I think it showed it in the parameters, but there's a section in here where they talk about non-trainable parameters. That's the kind of thing where someone would set like, oh, these pathways, I want to define them to be like this. Otherwise, you learn on your own kind of thing. Yeah. Hopefully that was helpful. Any other questions? We're still training. Yes.
How do you extract the why to better your training or your model?
Right. Yeah. This goes back into, I talked about we're using the Minecraft version of the data. If there's, more training. There's a lot of times the solutions like, oh, train it more, give it more data. Sometimes like I said, the increasing the resolution to give it more features to lock onto is the right answer. And sometimes it's just something that I haven't seen it a whole bunch, but there are instances where it's like this thing will never be able to tell the difference between these two things. What I've done a lot in the past, because I was talking to somebody about this, okay, what I have done in the past is I have intentionally tried to dupe a model by providing things that look very similar to a thing, but then saying this is not that thing. I hot dog, not hot dog it. And hopefully some people got that reference. If you can kind of try and you're teaching it, right? You're teaching it like what things to look for and how to find features that differentiate things. So if you put emphasis on the things that differentiate it and say, if you see a shirt and not a shirt, and a not shirt looks like more like this. The other option is to you can actually, one thing I've seen done is you can classify certain subsets and have basically like, oh, if it is one of these things, send it to a second classifier that's trained specifically to differentiate pullovers from shirts instead of pullovers from shoes.
Oh, this is see the difference between things, but this is a long sleeve t-shirt from a whole.
Yeah.
This is a whole other extra things.
No, you might be able to actually never tried anything. That would fall under like the non-supervised learning thing, but I haven't seen any I've never used that personally, but I'm sure it's probably out there because people are mucking around with this everywhere. It'd be very interesting to look into. And presumably, I'm going to go ahead and assume that modern transformers are doing probably a lot of that because they seem to be really good at inferring context, which is related more to recursive neural networks, which I touch on here. Recursive neural networks were still hard to get into embedded systems when I was into this, but recursive neural networks are good at understanding context for things. Typically more in the time domain, but you can translate those other dimensions. So, yeah. So there are ways to do it, and there's several ways to do it to skin that cat. Any other questions? We're coming up on our last epoch here with a 67% accuracy, which is just garbage. Okay.
Does it, in the final answer, does it also give like a percentage? Like,
yes,
I'm 90% sure this is a t-shirt, but it's 10% that it might be.
You're going to get a probability distribution on the output. So it'll basically be, here's an array of all the, I'm classifying between 10 different things, and you'll see a value in each category, and whatever one has the highest is basically the highest probability it has. But it's never, I've come across some ones where it's like, the highest is like 30%. It's like, okay, well, it's not great. And these are situations where you can start feeding them into other models or start using empirical rules for determining this differences between things that maybe the machine learning model wasn't good at picking up on, but you have context for outside of that. That's a rare case, but every now and then. All right, we trained up. Look at us with our 67% accuracy, just crushing it over here. Data augmentation. So when you have, when you have a bunch of data, you have like a bunch of images of cats and stuff like that, and it works really well with the convolutional neural network. When you're going to build your training data sets, you can take your raw data that you have, but you can also do a thing called data augmentation, where you take each picture and like stretch it out, or flip it upside down, or rotate it. Because what you're trying to do is teach the thing to lock onto features, not onto this is a cat that's facing left. You're trying to say a cat has eyes, and a cat has 4 legs, and a cat has more fur than another thing. Cats typically are these colors. So you're building all these feature sets, So if you can manipulate your data and present it to the model in ways that essentially seeing the same image but in a slightly different way, you can actually 10x, sometimes more, the amount of training data you feed into this thing and make a model better at generalizing. It's a really useful tool if you have a limited data set to work with. When I built mine, I was looking at, when I built the one that we use for our company, I was looking at accelerometer data converted into this, into the frequency domain, and then we were able to actually take that and stretch it and move it around, and it got the same great, I mean, like I said, 99.99993 accuracy on our classifications. So you can augment any data. All right, we're going to evaluate our model and see how this goes. Not looking good. 67%. Whew. Wow. Yeah, sorry. Yeah. Well, right now we're using Google servers.
Is there any specialized hardware involved?
You can hook TensorFlow up to video cards and stuff like that. I did all mine just onto video cards. It has capabilities to hook. When I did mine, I was just doing it on my laptop, sitting in Austin sweating. And I did it, you know, it would burn my computer up and I'd let it run for 24 hours, but then I'd come back and I'd be done. All right. But yeah, it could have been done probably in a fraction of the time if I had taken the time to put it on a proper computer. It was not.
So the neural network simulation is conventional computer program.
Yeah. Oh, no. Google and the company that I work for, Google developed their own silicon that they call tensor cores, which are designed specifically to take these models and process them. And then we kind of did the same thing, but we weren't allowed to call them tensor cores. My VP told me, or else we get sued. But you can very much implement these with hardware that expedite not just training these things, but also using them in a real world scenario to get quicker responses on your evaluation in HDL, in actual hardware if you want. Right, well, we predicted a cat, we got a cat. Apparently it's a cat. I wasn't expecting that. Okay, so let's look at this. We got our confusion matrix. So we got a lot of confusion between, looks like cats and dogs, both bipedal, pretty similar in structure. And this brings me to one of my favorite memes of all time. Oh, shoot. Media saying the whole AI took over the world. My neural network, dog. Okay. Recurrent neural networks. Okay. So recurrent neural networks before ChatGPT and all those transformers are around were basically the go-to for sentiment analysis and for evaluating human language and things that require context, time domain, looking for sequences that classify as a particular thing. The best example I can give is we're going to build a little IMDb review classifier here. But you can see right here we have two reviews that are very similar but have very different context. I hate how much I love this movie, and I love how much I hate this movie. CNN would not be able to figure out the difference between those two things. It would be like, yeah, it's got all the features that I'm looking for. An RNN can look at the sequence they're happening in and say, yeah, these all have the same words, but the order that they're in matters very much in this context. Sentiment is completely different. It all comes down to word order, statefulness. RNNs have statefulness. And you could use this for video, for analyzing video, any kind of time series data. Anything that has a one state will result in the next state, and if that state is buried, the output is something completely different. Classifying video as being running forward versus backwards would be tough, but it's still RNN would be better suited for it. So we're going to build a simple RNN for text classification. This is like the only easy demo I could do of this one. We are essentially going to create an RNN model. We're going to feed in an IMDb database of many, I forget how many IMDb reviews, different movies that are all labeled as I like this movie or I didn't. And then we're going to try and analyze reviews that we haven't seen and figure out if the review was good or bad. We're getting our data here from the IMDb database. splitting it into training and testing. What's going on right here with the padding, essentially what we're doing and this goes back to neural networks are only working on data. And the more you can simplify the data, we're basically Minecrafting our word data. Instead of feeding an entire word into this model, we're looking for every unique word and assigning a value to it and just feeding in sequences of those numbers. So we're tokenizing everything. And then we're setting a max length because the dimensionality feeding into the model has to be the same. So we're padding it with zeros if there aren't words in there. And the model knows to ignore those. It'll just essentially ignore them as not being features. Actually, it might be picking up on zero presence as features. Anyways, we're defining our model. Did we do everything here? We did. Defining our model, simple RNN, model sequential. We're putting an embedding layer in it, and we're defining the simple RNN. Explain right here what all the different parameters are for. You feel free to read through them if you get a chance. I'm starting to get up against my time limit here, and I'm trying to make sure you guys get everything out of this course as you possibly can. We're compiling the model, check. Now we're going to train the model. This one takes a long time, and I should have started that before I started talking about RNNs. More questions? If anybody's got it. I'll go left to right because I'm from America.
I think one of these workbooks,
Right.
how do I get this done?
I get to that at the end of the presentation. TensorFlow has a package. They have a workflow where you can take the model you've trained here, which, so right here we've done model.fit. After this is run, there's a model.compile, not compile, it's export, and essentially it will export. You specify this is for a embedded system, and it will export the file as a module you can drop into a TensorFlow Lite architecture that you can put on a bare metal system. I ran on a smartwatch, right? It can get on small stuff, and then you just start feeding data. The hardest part about that usually is doing all the formatting for the data in Python, and then turning around and having to do that in like an embedded system. Like we're reducing, like reducing dimensionality, changing array shapes and stuff like that, normalizing the data. That gets tough, obviously, in an embedded system more so than it would be in Python. I can do it in one line in Python, and I'd probably spend 3 days working on it in embedded C. And in HDL, it's an even bigger pain in the butt, but it is doable. But yeah, so you can drop them into an embedded system. Yes, sir. Oh, the question was, how do you take the model that we're training right now? Can they hear me? How do you take the model that you're training right now and drop it into like an embedded system? And that is how. And like I said, at the last startup that I was at, we took some of these and we dug into the underlying code because it's all in Python, and we built our own tensor cores out of it. I'm not allowed to say tensor core. I should not have done that on camera. We didn't end up using them, so it's fine. But yeah, so TensorFlow has a workflow to basically drop these into any embedded system. And if you have a Raspberry Pi, you're way set because you can just take the Python model, export it, save it over there, and open it up over there right in Python. But if you wanted to build into a even smaller package, have it run snappier, embedded C, you can do that on the Raspberry Pi also, or on a smartwatch, or on Java. They basically have hooks to export it to any language, and really any language that's going to run on embedded systems like an Android phone, a smartwatch, a Raspberry Pi, anything.
So after you've trained a model, and let's say you've trained it to recognize like 10 things.
Yep.
10 images.
Yep.
And now you want to add another. Do you start from the other model? Do you start from scratch? How much?
That's a
How does it take to make that progress?
That's a good question. If you build a model, how hard is it to go back and add new stuff to the model? I'm not showing it here, but there are actual hooks in TensorFlow to preserve progress. Now, having said that, changing the output classifier layer might be, I don't know. I think it can reduce some of the training time, but typically adding new output layer stuff, I usually just tell people like, just start. The memorized stuff that's in the model that TensorFlow saved. It's kind of like if anybody's worked with Vivado and it compiles hardware for you and you try and reopen it later and it's not necessarily compiled all properly, and then you change the stuff and it doesn't jive properly. oftentimes in this case, like all the cache data that's saved for the training, you might be better off just throwing it out, depending on how much time that takes, right? Some of these larger models, at least for image classification, they've trained those first 50 layers, and these things do get to like hundreds of layers. They've trained those and they preserve that because they know that part works, and then they add new parts on the end and are able to basically expand upon those. It's like a git commit, right? It's like committed code that you can commit this cache layer block and then add parts to the output of it. It's hard to inject stuff in though. Like once you're tampering on the inside of that block, all bets are off. You had a question that I didn't get to?
Dimensionality. Like difference you go up or down. I mean, typically you lose proximity information and change dimensionality.
You'd think that. Dimension. This is a question again about dimensionality. If you basically eliminate dimensionality, take a 4D data structure and reduce it down to a single 1D array. Sometimes I have seen occasionally a model locked onto these dimensionality features, but largely my experience, this is my experience has been is you can basically just flatten everything, and usually it picks up on the relationships even between like this array index over here and this array index here. It's like, oh, I saw those in that same place everywhere. It may result in like more neuron pathways getting strengthened that you maybe didn't count on, but I haven't seen that personally, and I don't want to talk outside of my scope of knowledge here, but I think preserving dimensionality is good for it depends on the data a little bit, but in general you usually get just flat stuff. With a convolutional neural network, because it locks onto features, the dense neural network would not do well with that. So that's where convolutional is really good, because it locks onto sub features. It's focusing on like two little blocks on the array, and says like, oh, I have seen the presence of this thing in these two little in a 2x2. Yes, the dense is as per its name, a little dense. It can process things if it's seen a lot of things that look kind of the same, but the second you take that shoe and you put it in the same screen as like a shirt, now it's like, I don't know what this is. This is crazy to me. This is just a shirt with a shoe on it, maybe. Actually would be right. But anyways, yeah. So, and it's one of the things you can play around with too. It varies on the data. So you kind of get in, I tried flattening it and get great results. I kept the dimensionality. Oh wow, this works. There's something about this dimensionality for some reason that is building strong. And usually after you've seen that, you can kind of infer like, oh, I get why it's picking up this relationship. It's important because this needs to be in this proximity across these array dimensions. Yeah, hopefully that's helpful. It's experiment, fun, and still easy to do. You can just run it. You can run it, like run 2 4 epoch training things and see which one turns out better. Like, oh yeah, if I maintain the dimensionality, it works way better than if I don't. Yeah. Any other questions while we're coming up on we're on the 4th epoch. Yep. Oh, are you winning?
On this one, no, you're winning.
Okay. Yeah, no. Because a lot of how this is training is using random numbers in every training sequence. It's every time a neuron guesses what its results should end up being, that's completely random, and then it's rewarded essentially. The loss function is telling it like, oh yeah, the thing that what you guessed is right, and so it basically, because these are all random, that's the kind of the backbone of this too, is that a lot of machine learning is just the machine guessing randomly and seeing what sticks, which evolution, right? That's go for it.
Do you end up with many like local means or local answers, but then with confusion, it's like, well, actually the right answer is over here, but every time I moved in either direction, I was getting higher loss, and so therefore I get stuck in the local.
You'll see that in the reinforcement learning a little bit. Yeah, you do get weird stuff like that. I was asking if you get like local mins or kind of anomalies, basically, right? You get like anomalous data that kind of creates local mins and local maxes. Yes, it does happen, but it happens. The more you train, those get kind of washed away. It's pretty rare, but it's not impossible. Like he's getting different data than I'm getting, so I am seeing different result from mine. Are you winning yet, or am I winning? I got a 79%. I'm coming up on 88. It's pretty good. No cat dog in this one. This is a lot of work for just IMDb reviews, but it's pretty. Yeah, we'll see. So okay, and I talked about. I'm kind of getting over our time here, but I've just got one more thing to show. Hopefully, you'll enjoy it. Quick word about transformers, GPTs, or whatever it is that everybody's doing these days. They weren't really present in this library when I was doing this 4, 5, 6 years ago. So I'm not hip to what's going on in TensorFlow with these nowadays, but it is in there. And if you're feeling particularly froggy, you go ahead. A transformer is like a chat GPT. It's the large language models. It's admittedly, for me to speak with any kind of real authority on it, I wouldn't be able to, not coherently. I would recommend, it's essentially the transformer is essentially the backbone of all these large language models, and that's all I recommend. I don't want to speak to something I'm not astute on, and I think more people here are probably hip to this stuff nowadays. For me, I usually typically work in the signal processing area and classification stuff, so that's what I'm comfortable with. Having said that, like I said, the link in this presentation will take you to the TensorFlow transformer documentation, and have fun with this. But it's all here. I think this is code you can. Okay, it's not. But this will explain ad nauseum if you wanted to get into the weeds. And everything that I'm showing here today, this is all just a skim of the Google TensorFlow documentation, which explains every single one of these at a level of detail that will make you sick to your stomach, or you might enjoy the crap out of it. Pardon my French. But yeah, it's all these resources are available. Like I said, this is just a surface level skim. Oh, our model's trained. I got an 87 actually. That's not bad. Increasingly, loss is decreasing. Oh, wait. Our loss went up for a second. Model might have overfit. I didn't put any safeguards in there. We'll find out. And here's the reasons I'm not covering transformers. I have to understand transformers take a lot of time to train, even on Google servers. And there's a lot more, as you saw from that TensorFlow documentation page. If you thought that this presentation was in the weeds or heavy, it would have taken me hours to get through some of that stuff in there. All right, we're going to evaluate our model. We're going to feed in some training data it's never seen and see what happens. So now we're just feeding in a bunch of reviews and asking it to classify them as positive or negative, and we'll get a accuracy percentage on the output, and I'll show one of the reviews and see how it did. And I'm going a little bit over. Hopefully you guys can hang with me for 7 more minutes. I'll try and make this next part fast. Yes, sir.
What's the philosophical difference between accuracy and loss? They sound like inverse.
Basically, they really are. Yeah, you want to see your accuracy increase and your loss decrease. The loss is the amount of error that you're seeing. And accuracy, I know it is exactly basically the same. And yeah, they are usually correlated. Like if your loss starts to increase, well, no, that's not true. Your accuracy can stay really high and your loss can decrease and then start increasing. And that means that the model has memorized the data you trained it on. So now it's not good at generalizing. If you fed something that's never seen before, it's not going to know what it is because, like, oh, I've only ever seen. That's where you overtrain. And there are ways to get better. But that's like I've seen these pictures of these shirts, 50,000 times. So now I think all shirts are just this. When I see a new shirt, I'm like, I don't know. The features, it doesn't have the features that I'm looking for. Yeah. All right, so what do we got here? Test loss of 0.45%. That's not great. Test accuracy of 80.75. And we give this, please give this one a miss, BR, and the rest of the cast rendered terrible performances. The show is flat, flat, flat. I don't know how Michael Madison could have allowed this one on his plate. He almost seemed to know this wasn't going to work, and his performance was quite. So all you Madison fans, give this a miss. It must be, I don't know what give a miss is, but predicted as being negative. This is pretty good because last time I ran this, it did not get that right. So it looks like our accuracy is not bad on data it's never seen before. Once again, this all deals with statefulness and time domain relationships. But once again, dimensionality. Time domain is just a dimension that we're thinking about. Dimensionality could be any dimensionality that you think of. It could be related to, it could be data that's not even related to each other. You could have audio correlated to video data, and as long as you normalize it all and put it in the same array, it can build feature representations based off that. All right, reinforcement learning. So this is the classic, I'm going to teach my computer to play Mario Brothers, which is a really involved application. But essentially what you're doing is you're taking an agent, an AI agent, and you're giving it an array of rules to use in certain states. So it says, I'm Mario. If you've never seen any of this trained out, it's really funny because essentially the computer will the model, the files are in the computer. The model essentially kind of randomly, but also based off a rule that you set, decides whether it's going to take a random action or an action that is guided by past experience. And over time, it builds that past experience matrix up so that it gets a really well-defined set of rules for how to complete a task, a reward-based system. There is a lot of math in this one. I'm going to skip over a lot of it, but you're welcome to get into it on your own. We have agents, so that's our Mario. We have the environment, that's the level. With state, that's where Mario is standing right now, and that also includes this dude being here. Action, that's one of the many buttons that's going to get pushed to make Mario do the next thing. Reward is Mario not dying, and if he gets to the end of the level, that's max reward. So those activities are rewarded. Policy, that's essentially the rule set that the agent, the Mario, uses to determine what to do in its current state. Value function is a prediction of future rewards that help the agent evaluate different states and actions. So this is essentially the notion of the action that I take will reward me short-term versus achieving a long-term goal. And Q learning function, which is the function that helps the agent determine the best action to take in a given state by estimating the expected future rewards. So this is essentially splitting the big premise in this particular Q learning model is it's balancing long-term rewards versus short-term rewards through learning. And once again, I talked about there's this RL1 is a Markov decision tree or this hidden Markov model-based learning process. This depends heavily on state and time domain and going from one state to another and inferring things about the state without being able to see the state long-term. Q learning, this is talking about how to populate these arrays and how they get updated. I'm skipping over a lot of this. I'm trying to keep under time here, or at least close to not super over time. Here's the formula for how you update your Q state array. This is really heavy stuff if you don't do any math ever. To just know that it's essentially a mathematical function that tells the model how to learn and how based on rewards. And you can define these values to make it learn faster or slower or learn smaller or bigger based on the action you take. The example we're going to do is called frozen lake problem. Essentially, we're going to create a, I have to run a different version of NumPy for this. Don't worry about that. It's just some nerd stuff. Okay, so what we're going to do here is, I'll show you the stuff. If you're running this at home or here, it's going to prompt you to restart if you load this NumPy thing. It's fine. But that's the reason I had the issue earlier. Just because I'm running, it locked into an older version of NumPy. Okay. So what we have essentially is, here's our frozen lake. The character starts here. We have a hole here, a hole here, a hole here. That starts to have frozen sections. We're trying to get to the goal. We're going to be able to proceed. We're basically going to tell the agent to proceed through this maze and then reward it based on whether it gets to the goal or whether the action it's taken gets it closer to the goal through a series of steps. And then we're going to iterate that over and over and over again to essentially teach it, give it a core learned behavior for the actions that will reward getting in any given state that will reward the agent at that time and get it closer to the goal. Okay, we built out here. This one's really hard to show well. because I don't have a good graphic user interface. It's just text. So bear with me here. We have values that represent different actions. And so we have the different states, or the different states that the agent can be in, which are these, the different characters for each panel. Okay, so we're going to advance the state. So what we've done here is in each one of these, you see I take a sample, which essentially advances the state in a random direction, and then I'm rendering it. So right here we see I have. Sorry, that's not a good graphic representation. This is all going to be in the piece of array. So at 0, 0, we tried to go up, nothing happened. Tried to go up again, nothing happened. We're going to do random. So in that corner, there's not a whole lot that can happen. He's going to go right or down. If he doesn't do that, he won't get rewarded. Does go right. Puts him at the at this second frozen spot up here. Once again, it's not a good way to show this because you have to basically track where the row and column even is. If I had better, it's just not a good environment to show this without creating some kind of GUI. But here we are. So we've advanced him several random states. He's not really building a rewarder now. I'm just showing you how you can advance the steps manually. What we're going to do now is we're going to train the model by basically having the agent do this over and over and over again, stopping if it falls in a hole, not getting rewarded for that sequence, not learning that behavior. Okay, so resetting our Q matrix right here, which I kind of touched on earlier. Once again, time constraint. If you want to get more into the math of how this is working, feel free to go back into the presentation on your own time. Okay, we're defining some parameters. So we're saying run this 2,000 times. If you get stuck and you've taken 100 steps and you've not reached the goal and you haven't fallen in a hole, just quit. Here's the learning rate we're setting for our Q matrix update. And we are setting a gamma discount factor. And this is how much the agent balances long-term rewards versus short-term rewards. Okay, and essentially that will define whether it picks a random action or if it uses the Q table to try and guide itself toward the exit. So it's essentially we can guide how aggressively it learns. This can result in weird behavior. I've found, not that I've done a bunch of this, but I found that the more iterations you give a process to kind of learn, the more the behavior that comes out is like what you would write. And once again, this comes back to machine learning is good for generating rules for stuff that it's hard to write rules for. Very easy to write rule sets to tell this little guy, don't step in the hole. But if the map suddenly turned into at like 1600 by 1600 square and also goes across 3 dimensions, so there's different layers to go to, it's a little bit harder for a human being to write the rules for that. But given enough time and iteration, it can be relatively easy for a reinforcement learning agent to learn these rules and kind of figure stuff out that we wouldn't be able to write. So it's good for writing algorithms that would be difficult to define empirically. Okay, so this is the function defining the random action. We're going to put it all together and we're going to train this dude. And away he goes. Okay, so we have a Q table here that's been defined. Average reward over 1,500 episodes was 0.28. So what this is showing, so this, once again, this is a really ham-fisted example to use. But essentially what this is showing, let's make it this right. Okay, here we go. So this model is learning the long-term expected value of taking each action in each state. So if example, if you look in, if the agent is in state 13, Q13, and the value in that row was 0.9, 0.09, 0.08, 0.83, and 0.03, it knows that if I go to the right at this position, I have a higher probability of surviving than if I go in the other direction. But even though if we look at state level 13, I'm sorry, this is a lot. I know we just got into, now we're looking at arrays and counting indexes. So that's right here. So right here, his goal is to the right. And as we saw earlier, it's a 0.83% chance of success if he goes to the right. but he could still go to the right. We're balancing random actions versus long-term reward. That agent can go to the right and then still right back to the left. It's not 100%, right? He could, the random action component of it means that he could get over there and do the thing that would get him killed. The longer you train that, the higher those probabilities get. It'll learn like, oh, there's a 99% chance I go to the right and I survive as long as I don't do anything stupid over here. I know I'm assuming a lot of human characteristics to the thing, but once again, this training method and this reinforcement learning in particular is really modeled off after how we learn as humans and how we train animals and just the learning process in general. So it's just that the computer can be a little bit more random at things. Okay, so reinforcement learning, you said there's a lot more math in that one. Feel free to go in on your own time and dig into it. I just want to give you guys a sample of it, show you how it's kind of applied. Putting it all together, we train the model. We have the Q learning table. Okay, we're at the end of the presentation. Would you like to know more? You totally can learn more. At the end here, I learned all this stuff. Like I said, I came up at my last startup. I came up with a concept problem. We had 3 PhDs on our team. We couldn't solve this problem for like 2 years, and I just I kind of took some time after work and found this 16-year-old kid's video on explaining TensorFlow 2.0. It's a 7-hour course, basically 7 hours of everything I just told you, but way more detail. And I learned everything that I know from this kid who's gone on to be like an incredible, like known programmer. A really great video, a little bit dated at this point, but if this was exciting to you, I recommend the next step is go watch his video, sit through the 7 hours of it, really rad. And then if you want to know even more, then you go to the official TensorFlow documentation where everything I just talked about is explained. I showed you the transformer stuff. Everything I just talked about is explained ad nauseum in there, and that levels of detail that will maybe give you insight that I wasn't unable to provide for you tonight. But my whole goal here tonight was to give you these tools so that you can take this stuff and go out and make new technologies or new applications that maybe you can roll into products that the companies work for, or just build for yourself. Maybe you just want to make your Roomba smarter and you learn how to hack it. Go for it. You have the tools now. You just have to learn how to compile the data. And there's stuff in here about TensorFlow Lite if you want to know it. And this is the end. Thank you guys so much for sitting through that. Yeah. And is there any questions real quick before we get, or you can talk to me offline because we're definitely over time, right?
Yeah.
Okay.
Matt, we appreciate so much you put this together.
Oh, thank you.
Yeah, so thank you very much for that.
Thank you so much.
And I think a great part of this isn't just the presentation, but you left us with a tutorial.
Yeah.
Which has got a ton of information in it. So I know you presented a lot of material quickly, but it's great that you created this document for us to go back.
Yeah.
Thank you.
Feel free.
Yeah.
And hopefully somebody gets this right. All right. Thank you guys so much. It's been awesome.